Okay, welcome back, kiddos. Today we're going to apply the things that we've learned in gas laws to a little bit of stoichiometry. If you guys recall stoichiometry from an earlier unit, it's the mathematics of a balanced equation. And once again, we'll be doing the mathematics of a balanced equation, but we'll be applying gas laws as we do so. It's not too hard. Buckle in and enjoy. Pay close attention, take careful notes. You're going to see that your homework is going to be pretty doggone similar to the problems that we work here. Okay? So here we go. In example 5 from your notes, you can see we have a nice, pretty balanced equation. Now, you might have to balance that on your own, so please keep that in mind. Don't expect these equations to be automatically balanced for you. Now, I want to know what volume of hydrogen gas, so it doesn't say gas here, but it's implied, that can be produced from 3.17 grams of aluminum reacting at STP. So aluminum metal will react with hydrochloric acid to produce hydrogen gas and aluminum chloride. You sharp kids that are on the ball and probably thinking ahead of me realize that, hey, that's a single replacement reaction. Aluminum and hydrogen switch positions. So hydrogen is produced and aluminum gets together with chlorine. Aluminum's 3+, chlorine's 1-, so it's an AlCl3 product. Okay, so here we go. We have 3.17 grams of aluminum. And so, of course, we need to go from grams to moles. So remember, once we have our balanced equation, we go from grams to moles. That's sort of what we've been doing in our other stoichiometry problems. And aluminum has an atomic mass of 26.98 grams per mole. All right, so that gets me out of grams of aluminum into moles of aluminum. And I want to find out about hydrogen gas. So let's put moles of aluminum on the bottom to get rid of it. Put moles of hydrogen gas on top. That's what we want to get into. Do you guys remember what we put in here? That's right. We put the coefficients from the balanced equation. So there's a 2 in front of Al. So we put 2 moles of aluminum and a 3 in front of H2. So 3 moles of hydrogen. So it's a 2 to 3 mole ratio. So that gets me into moles of hydrogen. Now, we want to know what volume of hydrogen can be produced at STP. So I want to hop out of moles of hydrogen, and I want to get into liters of hydrogen gas. Now, I can use this special conversion factor only if we are at standard temperature and pressure, which we are. I set that guideline for you. We are at STP. So what is that conversion factor that will allow us to go from moles of any gas to volume, to liters of that gas at STP? That's right, 1 mole of any gas has a volume of 22.4 liters of that gas. Okay, so long as we're at STP. So, we're done. We just need to do the math here. We'll pull out our cheap calculator this time and see if you guys can plug and chug with me. 3.17 divided by 26.98 times 3 divided by 2 times 22.4 equals 3.95. Looks like we're allowed 3 sig figs. 3.95 liters of hydrogen gas will be produced at standard temperature and pressure if we have 3.17 grams of aluminum, and of course hydrochloric acid is our excess reactant. Okay, not too bad, is it? Well, what if we're not at STP? Well, we're going to worry about that in just a little bit. Not quite yet. We're going to ease on into it, but start thinking, hey, what if we're not at STP? How would we handle this? Just start thinking about it. We'll get there. Okay, second reaction, or second problem, example 6. How many grams of potassium are needed to produce 42.6 mils of hydrogen at STP? Whew, we're at STP again. Cool. So let's balance this guy. You can see it's not balanced. 1 potassium, 1 potassium. We've got 2. The hydrogens don't balance. We've got 3 on this side and only 2 on that side. Let's do this. Let's put a 2 in front of KOH. Now what that's going to do for me is, yeah, it's going to give me 2 potassiums, which I have to fix on the other side. But so you have 2 plus 2. I have 4 hydrogens, so I can put a 2 in front of H2O. That gives me my 4 hydrogens that I have on my product side. Gives me 2 oxygens that I also have on my product side. So it's balanced now. Pretty cool, isn't it? All right, so let's see. We're going to start with what I'm given. 42.6 milliliters of hydrogen gas. Now that's at STP, kiddos. So what do we know? Well, we need to get into moles. We're going to get out of milliliters of hydrogen gas and get into moles of hydrogen gas. Now, 1 mole of any gas has a volume of 22.4 liters, but we're in milliliters. No big deal. That would be 22,400 milliliters. Now, I could have converted from milliliters to liters first, but that's pretty handy to know that there are 22,400 milliliters, which are the same as 22.4 liters. Okay, so we've got out of mils of hydrogen gas. So we're going to go from moles of hydrogen gas into moles of what we're after, which is potassium. Okay, and what's my mole ratio? Let's see, there's no number in front of hydrogen, so that's 1 mole of hydrogen gas will need 2 moles of potassium. Okay, so I've gotten out of moles of hydrogen gas and into moles of potassium, and we want to know grams, so we're going to go from moles of potassium to grams of potassium. So let's look up the atomic mass of potassium here, 39.098, which rounds off to 39.10 grams per mole. Okay, so it looks like we're done. I just have to plug and chug, and you guys can do that right along with me. So we'll clear what we have out there. So we have 42.6 divided by 22,400 times 2 times 39.10. Let's see. I'm not too... let me plug that in again. 42.6 divided by 22,400 times 2 times 39.1. Okay, let's see what we get here. We get 0.149 grams of potassium that will react. Okay? Alrighty. Let's take a look at example 7. Oh, now we're collecting something over water at 26 degrees Celsius and 680 millimeters of mercury. And we want to find out how much oxygen can be produced there. So that one's going to involve me finding the vapor pressure of water. Because when we collect a gas over water, don't forget that we have to subtract out the vapor pressure of water in order to find the pressure of what we call the dry gas. So I'm just going to do a quick search here for vapor pressure of water on my computer. I'm working obviously right next to my computer. And you guys can do this at home. When you guys do your homework, you can find a vapor pressure of water table. And I just Google that, or use whatever search engine you want. And let's see, vapor pressure of water, here we go. And let's see, mine's at chem.oakstate.edu. And it's a nice vapor pressure of water. It gives me temperature and the vapor pressure of water in millimeters of mercury. Okay? So, we'll be using that information in just a second. Okay? So, golly, we're not at STP this time. We're at 26 Celsius. We're at 680 millimeters of mercury, and the thing's collected over water. Well, this is as ugly as she gets. If you can follow this one, you can do any one. Okay, let's balance this quickly. I want to put a 2 in front of KClO3 and a 2 in front of KCl and a 3 in front of O2. And that takes care of me. Now, I have 1 gram of KClO3 that I am working with. So I'm going to start with that, 1 gram of KClO3. We're going to go from grams to moles of KClO3. So we've got to figure out the formula weight of that, and I can do that quickly for you. I know you guys can do it on your own, but we'll work on it together really quickly. So we have 1 potassium. Potassium is 39.10. We have a chlorine. We have one of those. It's 35.45. And we have 3 oxygens, and that would be 48.00. So that gives me a formula weight of 122.55 grams per mole. Please check my math. I would hate to make a mistake here. but I feel pretty confident about that. Now we need to go from moles of what we know, which is our KClO3, into moles of what we're after, which is oxygen gas this time. Okay, so we've gotten out of grams, we've gotten out of moles of KClO3, and the mole ratio is 2 to 3. 2 to 3. So that allows me to get into moles of oxygen. Now if I were to stop right here, kiddos, I would have N of oxygen. I don't want moles of oxygen, I want volume. So we have to work a little bit of Pivnert here. Wouldn't V equal N, which we now know, if I were to stop my calculation here, times R times T divided by T? Sure would. So I've got the N part of that. Let's go ahead and multiply this answer now by 0.0821 liter atmospheres per mole Kelvin. Now that gets rid of moles of gas, so I've taken care of R, times T. Now my temperature is 26 Celsius. Let's not use 26 Celsius. Some of you guys made that mistake on a recent exam. You forgot to convert your Celsius to Kelvin. 26 plus 273 is 299 Kelvin. So there's my temperature. And then we need to divide by my pressure. Now, we have 680 millimeters here, but we're going to subtract out the vapor pressure of water at 26 Celsius. So, I looked that up for you, and the vapor pressure of water at 26 degrees Celsius is 25 millimeters of mercury. So we're going to subtract out 25 from that. And of course, that's millimeters of mercury here. Now that right there is the vapor pressure of H2O. And that either has to be given to you, or you're going to have to look that up. Now let's see. I have a small problem here. My kelvins cancel out, but my atmospheres do not get canceled out by millimeters of mercury. So one more step. We need to hop out of millimeters of mercury and get into atmospheres. And we know that conversion factor. 760 millimeters of mercury is 1 atmosphere. So now my atmospheres are gone, my millimeters of mercury are gone. The only unit I have left is liters. So always include your units when you do these problems. You can avoid so many silly mistakes if you include your units. All right, so let's plug and chug. We have 1 divided by 122.55 times 3 divided by 2 times 0.0821 times 299 divided by 680 minus 25, which is 655, times 760. Now, if I plug that all in correctly, I get 0.349 liters of gas would be produced. So that's how we handle it if we're not at STP. We have to employ PV equals nRT, and we solve for the variable that we're looking for. In this case, it was volume. Okay? All right. Let's move on to the next problem. We got a couple more here. Don't know if we'll have time to do both of them. We'll get at least one more done for you. Example number 8. How many grams of nitrogen gas are needed to produce 50 liters of ammonia? And we're not at STP again. 1.25 atmospheres and 500 Celsius. How are we going to get into moles here? I don't have grams. I have to find grams. So how do we get into moles? Could we do the number of moles of a gas equals the pressure of that gas times the volume of that gas divided by R, which is a constant, and the Kelvin temperature of that gas? I think we could. So let's do that. P is 1.25 ATM. And my volume is 50.0 liters. So I've got P and V. I'm going to divide by R, 0.0821 liter atmospheres per mole Kelvin. Since we're dividing by R, the mole Kelvin pops up on top. And let's see, we're going to divide by the Kelvin temperature, which would be 773 Kelvin, not 500 Celsius. We've got to pop that into Kelvin. Let's go ahead and see what units divide out. Kelvins are gone, atmospheres are gone, and liters are gone. So I have moles of my ammonia, don't I? I have moles of ammonia. If I were to stop my calculation right here, that would be moles of ammonia. I don't want moles of ammonia. I want to get out of moles of ammonia, so I'm going to do that in my next step by putting it on the bottom and get into moles of what I'm after, which is nitrogen gas, N2. Now what's that mole ratio? Is it 1 to 1? No, it's not. What didn't I do yet? I didn't balance the equation, did I? So let's put a 2 in front of NH3 and a 3 in front of H2, and that should balance it for me. So the mole ratio is 2 NH3s for every 1 N2. Okay, so now moles of ammonia are gone, and I'm in moles of nitrogen gas. And I want to find grams of nitrogen gas. I'm going to go from moles of N2 to grams of N2. And 1 mole of nitrogen is 28.02 grams per mole. Okay. All right. Let's plug and chug and see what we get, kiddos. Clear that out from before. 1.25 times 5, or 50, excuse me. That's 50 liters. Divided by 0.0821, divided by 773, divided by 2, so I'm right here, folks, times 28.02, enter. Looks like I get 13.8 grams of nitrogen gas. If I were finding the mass of that gas, that's how much would be produced. Okay? Alrighty. I think you guys can handle the next one. In fact, I want you to do that one on your own. This is 10 liters at STP. Okay? In fact, you know what? We could hammer this one out pretty quickly, I think. If we take a look at the equation, we have 1 nitrogen on both sides, 3 oxygen, so we'll put a 2 here and a 2 there. That balances it for you. You know what? On second thought, I think I'm going to have you guys finish this one off on your own. You're at STP, so that should help you out a little bit. And think about the law of combining volumes, which says something about the volume ratio being the same as the mole ratio. Think about that, okay? I'll have you do number 9 on your own. It's a lot easier than some of you guys are going to make it. All right? Hope you folks enjoyed this. We get to work a bunch of these in class and on homework. Good luck. Bye-bye.